Okay guys, so welcome back again to another video. In this video, we're going to talk about the stability of carbocation. So specifically, we are going to talk about hydrocarbons, right, and benzene ring structures. We are not going to talk about the amines and its derivatives. So we are going to do a separate video about it. First, let's look at these kind of stuff. And here I have drawn A, B, C, D, E, F, G, H. There are 1 2 3 4 5 6 7 8 structures, 8 carbocations. So we are going to order them into the stability. So I will explain how we can do this, what are the factors which we are going to look at, and what are the factors which are more important when it comes to the stability. Okay, so let me take this color. Okay, so when it comes to stability, always remember, okay, there are two factors with these R groups, or like CH3, CH2, CH3, like this alkyl group, these R groups, these guys can push electron density towards, right? So if you have a structure like this, you can see these guys can push electron density towards your carbocation. This carbocation means it has less amount of electron density. So if these guys can push electron density towards your carbocation, which means this positive charge will be somewhat neutralized. So this is the first way how we can stabilize the carbocation, by CH3 groups, the electron pushing effect. We call that conductive effect. So with this kind of thing, you can push electron density toward this CH2 plus carbocation, and you can decrease the amount of positive charge, so which makes this stabilized, right? And the other one is the resonance structure, right? So if you look at the example here, look at this one. So you can move this double bond to this position, right? Break this double bond and move it into here. So what happens now? So both these two carbons are going to be stabilized, but this case here, this carbon, this going to be take positive charge. So you can move your positive charge across your molecule. We call it as the delocalization of positive charge. By delocalization, you can stabilize the carbocation. So basically, this is much more effective than the normal electron push. Always remember, if you have, these are the main factors which we have to look about. From these two, you need to focus more about resonance structures. So let's say you have two molecules, one is showing the resonance stabilization, one is showing only the electron pushing. Then there is no doubt, choose the resonance stabilization. Which molecule give the resonance stabilization? It is much more stabilized than just the electron pushing effect. So let's move on with these structures, right? You can see now when it comes to this A structure, we have an electron pushing effect, but when it comes to the B structure, there is only one, right? This two comparison is pretty much easy, right? Because there is only one here to push, but there is two guys to push here, right? So but basically what happens is this CH3 here has no effect that much, right? There's a very tiny amount of effect. So we will talk more about this on advanced organic chemistry, like the only CH bond can donate the electron density towards your carbocation, right? So by having more and more CH3 groups here doesn't help that much. Yes, it helps, but very tiny amount. So there's a very tiny difference between those two, right? So if we compare this A and B, then A is more stabilized, but from very tiny amount. So if you look at here, you can see CH3, these guys are on both sides, right? So this stabilization is much more effective here. This electron donation is coming from both sides. So this neutralization of this positive charge is much more effective than this both two. So if let's take position A here, and you can see B is less stabilized than the A, and this C is stabilized than the A and B both. So here we have the C here. This is C, okay? So this guy is much more stabilized. So now you can see here, look at this one. This is resonance stabilized. This is resonance stabilized. So I have told you, if you have to compare a normal conductive effect and resonance effect, then there is no doubt the resonance effect wins. Due to these resonance structures, this positive charge can be delocalized. More resonance structures you can draw, more stabilized it gets. So in this case, you can only achieve 2 resonance structures. So which means, like, in this case, the D carbocation is much more stabilized than all of these 3. Okay. Now let's look at the E. You can see now E is the same like the D, but there are additional 2 CH3 groups. So like addition of these resonance structures, there are conductive effect too. So which make this a much more stabilized than this guy. So here I will put E on this position. Now we have F. You can see when it comes to the F, you don't see any kind of resonance structures. So there is no resonance stabilization. So definitely they will go below the E and D. Here look at this. So CH3, CH3, these guys are here. This, and also look at this. There are 3 ways to push electron density towards your carbocation. Here you have only one way, 2 ways. So this guy is stabilized than all these 3. So I can place it over here. It's reasonable, right? Here in C, you have 2 ways to stabilize it. Here you have 3 ways. So it definitely have to increase, this have to be in stabilized than the C, right? Because it has 3 ways to stabilize the nuclear charge. Okay, so now we have come up to here. Now we have benzene. If you know that benzene can form resonance structures. So if you remember, we can put this double bond to form 2 bonds within these 2 carbons and delocalize your positive charge into here. And you can put this positive charge all around your benzene. You can change it into here and here. So like 4 structures you can draw. So likewise, from the delocalization, always remember you can stabilize the compound. With the benzene in it, it is much more stabilized because the benzene ring is it has higher electron density. So this positive charge can easily neutralized by this benzene. So this carbocation is much more stabilized than every other which we have talked about. So I will put this G above everything else. Now we have the last one, H. You can see a benzene ring, but beware, like you cannot form the resonance structures here, right? You cannot form the resonance structure. Yeah, like you can move your double bond over here, but it cannot do because like there's a CH here. There's a CH here. Yes, like there can be hydrogen shifts, right? There can be hydrogen shifts. So let's not talk about the hydrogen shifts. Let's talk about just the carbocation, right? Let's just talk about the carbocation. If you see a carbocation like this, so like so if you are a little bit confused with the hydrogen shift, so I will add another CH2. If you have no idea about the hydrogen shift, methyl shift, like it's completely fine. But if you want to know about it, I will put a link here. So we have discussed the hydrogen shift, methyl shift, like things in our organic chemistry videos. So you can watch it and have a knowledge about it. So let's move on to this structure, right? So now you don't have to worry about the hydrogen shift. So you can see there's nowhere to form the resonance structures with this particular carbocation. Okay, this particular carbocation. So let's forget about the hydrogen shift, right? So this particular carbocation is just like here, just like this, because this benzene cannot form the resonance structures because the positive charge is not connected to your benzene. So if your positive charge is not connected to your benzene, then the benzene cannot help it because there are component here in the middle. So benzene cannot help this positive charge. So this positive charge cannot form the resonance structures. It cannot delocalize. Only thing it can achieve is the electron push from this R group. So this electron push is larger than this guy because there are more carbons, and also this guy because this guy has 2 carbons and this guy has much more carbon than this. But as I have told you, like this, this guy has 3 ways to neutralize this, but this guy has only 1 way. So like if you, it doesn't matter the length of your chain, right? But this, the matter is the direction. If you have 3 direction to neutralize your charge, it's much more stabilized. So in this case, I will put this H above here. This, our H molecule will, H carbocation will pass this guy and also this guy, but not this guy, So I can put it like here, right? So I will cut it open and put H on here. So this is the order which I have come up with. So always remember, these are the main thing which you need to know about. And also it doesn't matter where the benzene ring is present or not, right? You need to check whether the benzene can connect with your carbocation, whether it can form the resonance structures with your carbocation. Otherwise it won't help. So these are the main thing which you need to know about. So we will talk about the amine and carbocation with amine and its derivatives after some few mechanisms and examples. So like I hope you are okay with it. So feel free to watch our channel and playlist, which we have talked more about organic chemistry and physical chemistry, especially biochemistry. So we will meet in the next video.